Dear friends, today we are going to discuss CSIR net December 2013 Part C problem in the linear algebra topic. Today just 3 problems we are going to discuss. So this is the first problem. Problem number 68. For an n by n real matrix A, lambda belongs to R, set of real number, and a non-zero vector V belongs to R power n, suppose that A minus lambda I whole power k into V equal to 0 for some positive integer k. Let I be the n by n identity matrix. Then which of the following is or always true? The options are a minus lambda I whole power k plus r into v equal to 0 for all positive integer r. Option 2, a minus lambda I whole power k minus 1 into v equal to 0. Option 3, a minus lambda I is not injective. Option 4, lambda is an eigenvalue of a. So, this is a very simple problem. For an n by n real matrix A, lambda is the set of real number, lambda is any real number. A non-zero vector V in R power n, a minus lambda I whole power k into v equal to 0 satisfied for some positive integer k. I is the n by n identity matrix. Then a minus lambda I whole power k plus r into v equal to 0. How to check? So, a minus lambda I whole power k plus r, we can express a minus lambda I whole power k, a minus lambda I whole power r into v. So, we want to check it, a minus lambda I whole power k plus r into v equal to 0 want check panam. So, for that a minus lambda I whole power k into a minus lambda I whole power r into v. We want to express the a minus lambda I whole power k plus r into v. We can express in terms of a minus lambda I whole power k, a minus lambda I whole power r into v equal to 0. Already given that for the in the hypothesis, a minus lambda I whole power k into v equal to 0 for some positive integer k. So that this is equal to 0 obviously. Because of a minus lambda I whole power k into v is 0 for some positive integer. So this is obviously which is equal to 0. So that from this what is the conclusion? A minus lambda I whole power k plus r into v equal to 0. So option 1 is correct. For the option 2, a minus lambda I whole power k minus 1 into v equal to 0. We want to check it, a minus lambda I whole power k minus 1 into v equal to 0. Suppose when you take that k equal to 1, a minus lambda I whole power 1 minus 1 into v equal to, what is that? A minus lambda I whole power 1 minus 1 is a minus lambda I whole power 0. A minus lambda I whole power 0 value is 1. Anything power 0 value is 1. So this value is 1. So 1 into v equal to 0. So from this, when you take k equal to 1 in the second option, we get it v equal to 0. We get it v equal to 0. Already discussed in the hypothesis, in the given problem, the v is non-zero vector. V is the non-zero vector. But when you take the k equal to 1 in this a minus lambda I whole power k minus 1 into v equal to 0, we get the v is the 0 vector. So this is a contradiction to our hypothesis. Okay, our assumption in the problem. So that option 2 is incorrect. Okay. The third one, for option 3, a minus lambda I is not injective. A minus lambda I is not injective. Okay. So for that, for the third option, I will take it since a minus lambda I whole power k into v equal to 0 for some positive integer k. This is the hypothesis. The given problem, given that a minus lambda I whole power k into v equal to 0 for some positive integer k. Lambda belongs to R. and a non-zero vector v belongs to R prime. These are hypotheses. நம்முடைய ப்ராப்ளத்தில் கொடுத்திருக்கிற datas. From this, a minus lambda I whole power k into v equal to 0 for some positive integer k. From this data, we can conclude the determinant of a minus lambda I whole power k equal to 0 by the definition, basic definition of the eigenvector. How to define the eigenvector a minus lambda I into v equal to 0. The v is the non-zero vector, that is, then v is the eigenvector. Okay, v is the eigenvector corresponding to the lambda, corresponding to the eigenvalue lambda. So from that definition, so on the eigenvector nude basic definition irundhu determinant of a minus lambda I whole power k equal to 0. Okay, we can conclude determinant of a minus lambda I whole power k equal to 0. So how to get it? This one from the basic definition of eigenvector. So from the basic definition of eigenvector, v is the non-zero vector satisfying the a minus lambda I whole power k into v equal to 0. From this, lambda is the corresponding eigenvalue to the eigenvector v. So that lambda is the eigenvalue. So then basic definition of the eigenvalue, determinant of a minus lambda I equal to 0. So determinant of a minus lambda I whole power k equal to 0. Okay. Then which is implies determinant of a minus lambda I whole power k equal to 0. Then which is implies determinant of a minus lambda I whole power k equal to 0. Okay. So determinant of a whole power k equal to 0, then which is implies determinant of a power k whole power determinant of a power k equal to 0. So inge determinant of a power k equal to 0, which is implies determinant of a whole power k equal to 0. So determinant of a minus lambda I whole power k equal to 0, which is implies determinant of a minus lambda I equal to 0. So whole power k, kth power is 0. Then determinant of a minus lambda I equal to 0. From this, what is the conclusion? There exists some non-zero vector v. Okay. Once again definition, any definition, eigenvector definition. This is the eigenvalue. Okay, how to define the lambda is the eigenvalue. Then determinant of a minus lambda equal to 0. Okay. So for some non-zero vector v belongs to R power n such that a minus lambda into v equal to 0. V is the non-zero vector. Lambda is the eigenvalue. So v is the non-zero vector corresponding to the eigenvalue lambda. Okay, just நாம் என்ன பண்றோம், eigenvalue eigenvector definition யூஸ் பண்ணிருக்கோம் இதுல. அவ்வளவுதான், வேற எதுவும் இல்ல. Okay, so the nullity of a minus lambda I into v equal to 0. A nullity of a minus lambda I v equal to 0. Inge there exists the non-zero vector. There exists some non-zero vector v satisfying a minus lambda into v equal to 0. Because of this is the definition of eigenvector. But when you use the nullity concept, nullity of a minus lambda into v equal to 0. From this, what is the conclusion? Nullity of a minus lambda I. Okay, this is not a v. Okay, so a minus lambda I is not equal to 0. From this, what is the conclusion? Nullity is not equal to 0 na ஒரு set of matrix non-zero vector satisfy பண்ணதுன்னு அர்த்தம். அப்படின்னா 1 to 1 கிடையாது. That is not injective. A minus lambda I is not injective. Is not injective. Okay, ஏன் not injective? So for some non-zero vectorக்கு இது satisfy ஆகுது. அப்படின்னா solutions நிறைய இருக்கு, நிறைய solutions இருக்கு. ஓகேவா? So a minus lambda I is not injective. ஓகேவா? nullity solution space is not equal to 0ன்றதுனால a minus lambda I is not injective. So option 3 is correct. Okay. The option 4, lambda is an eigenvalue of a. This is obviously true. Already discussed the determinant of from the given data. From the given data, a minus, we get it the determinant of a minus lambda I equal to 0. From this, lambda is an eigenvalue of a. Lambda is an eigenvalue of a. So therefore, option 4 is correct. Option 4 is correct. Okay. The next problem, problem number 69. Let s from r power n to r power n be given by v to alpha v. The v to alpha v for a fixed alpha belongs to r. Alpha is not equal to 0. let t from r power n to r power n be a linear transformation such that b equal to v1, v2, vn is a set of linearly independent eigenvectors of t. Then the matrix of t with respect to b is diagonal. First option. The second option, the matrix of t minus s with respect to b is diagonal. Third option, the matrix of t with respect to b is not necessarily diagonal but upper triangular. Fourth option, the matrix of t with respect to b is diagonal but the matrix of t minus s with respect to b is not diagonal. Okay, this is the idea. So it's also very simple problem. How to find out the solution? So this is the very simple problem. So easily we can find out which one is the correct option. So the first of all, given data s from r power n to r power n be given by v2 alpha v for a fixed alpha belongs to r. Alpha is the any real number, alpha is non-zero real number. V equal to, I will consider the first of all v is the standard basis. V equal to e1, e2, en. E1, e2, en are the standard basis of r power n. Then s of v is defined as v is tends to alpha v. So s of v equal to alpha v. Then alpha e1, alpha e2, alpha en. Alpha e1 means alpha 0, 0, 0, 0, 0. Alpha e2 means 0, alpha 0, 0, 0. Because of e1 is 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0. En is the nth position is 1, otherwise 0. Okay, these are the standard basis. In the standard basis, when you multiply the alpha, we get the alpha 0, 0, 0, 0 alpha 0, 0, 0, 0, 0 alpha something 0, 0, 0. Yeah, alpha en means nth position is alpha, otherwise 0. So the matrix of S, we get it the alpha 0, 0, 0, 0 alpha 0, 0, 0, 0, 0 alpha 0, 0, 0, and n minus position, n minus 1th row, n minus 1th position is n minus 1th position is alpha, otherwise 0. The nth position is alpha, otherwise is 0. Okay, so t from r power n to r power n be a linear transformation such that, okay, this is the matrix of S. T from another hypothesis, t from r power n to r power n be a linear transformation such that b equal to v1, v2, vn is a set of linearly independent eigenvectors of t corresponding to eigenvalue lambda I of t. Okay, these are set of linearly independent eigenvectors. That is the given hypothesis. So from this, v1 is the one of the eigenvector. This is corresponding to some eigenvalue. That is, I will consider as the lambda 1. v2 is the another eigenvector. This is corresponding to another eigenvalue. That is lambda 2. vn is the corresponding to eigenvalue lambda n. So that this set of linearly independent eigenvector of t corresponding to eigenvalue lambda I of t. Okay, the given hypothesis only the set of eigenvector, linearly independent eigenvectors of t. I will choose the corresponding, these are corresponding to some eigenvalue that is considered as the lambda I. Okay, so நம்முடைய hypothesisல இது மட்டும் தான் கொடுத்திருக்காங்க. b equal to set of linearly eigenvector னு கொடுத்திருக்காங்க. நான் ஒவ்வொரு eigenvectorம் corresponding to some eigenvalue னு அஸ்யூம் பண்ணிக்கிறேன். அவ்வளவுதான். Okay, from this, when you use the basic definition of the eigenvector, t minus lambda I into vi equal to 0 for all I equal to 1 to n. From this, t of vi equal to lambda I vi. T of vi equal to lambda I vi. From this, t of v1 equal to lambda 1 v1. T of v2 equal to lambda 2 v2, T of v3 equal to lambda 3 v3, T of vn equal to lambda n vn. Since b is linearly independent set, so b is also the basis of r power n. Since b is the linearly independent means the b is also considered as the basis of r power n. From this we can construct the matrix corresponding to b. So t of v1, v2, vn, v1 goes to t of v1 and this is v2, t of v2, t of vn. From this, t of v1 is lambda 1 v1, t of v2 is lambda 2 v2, t of vn is lambda n vn. Okay, so the matrix of t, what is the matrix of t? Matrix of T is lambda 1 V1 means lambda 1 and lambda 2 here lambda 3 and so on lambda n minus 1. This is the lambda n. Because of these are bases. Lambda 1 V1 we want to express in terms of V1, V2, Vn. That means lambda 1 V1 plus 0 lambda 2 0 V2 plus 0 V3 plus and so on 0 Vn. The same way lambda 2 V2 when we express in terms of the lambda V1, V2, Vn, because of V1, V2, Vn are the basis of R power n. So lambda 2 V2 when we express in terms of V1, V2 and so on Vn, 0 V1 plus lambda 2 V2 plus 0 V3 plus and so on 0 Vn. The same way when we express the each and every lambda n Vn, we get it the corresponding coefficients form a matrix, that is lambda 1 0 0 0, 0 lambda 2 0, 0 0 lambda 3 0, 0 0 lambda n minus 1, 0 0 lambda n. So this is the corresponding matrix of T corresponding to the basis B. சரியா புரியுதா? அந்த Bன்ற மேட்ரிக்ஸுக்கு கரஸ்பாண்டிங்காக மேட்ரிக்ஸ் கன்ஸ்ட்ரக்ட் பண்ணுறோம். ஸோ அதனால் lambda 1 V1 எக்ஸ்பிரஸ் பண்ணலாம். எப்படி V1 V2 Vnல எக்ஸ்பிரஸ் பண்ணலாம். அதனால் 0 lambda 1 V1 plus 0 V2 plus 0 V3 and so on அது மாதிரி எக்ஸ்பிரஸ் பண்ணிங்கன்னா உங்களுக்கு இந்த மேட்ரிக்ஸ் கிடச்சிடும். அது ஒவ்வொன்றுத்து கோஎஃபிஷியன்ட்டையும் இந்த காலம் வெக்டராக எக்ஸ்பிரஸ் பண்ணிங்கன்னா we get the corresponding matrix. Okay. From this இது ரெண்டுத்தையும் கன்ஸ்ட்ரக்ட் பண்ணிங்கன்னா ஆன்சர் இஸ் ஓவர். So the matrix of T with respect to B is diagonal. The matrix of T is with respect to B is diagonal. So option 1 is correct. So matrix of T minus S, just subtract the matrix of T and matrix of S. So we get the lambda 1 minus alpha, lambda 2 minus alpha, lambda 3 minus alpha, lambda n minus 1 minus alpha, lambda n minus 1. So matrix of T minus S with respect to B is also diagonal matrix. So option 2 is correct. What about the other options? Other options are not true. Because of these two options are true, other options are obviously not true. Okay. The next problem, problem number 70. For any real square matrix M, let lambda plus of M be the number of positive eigenvalues of M. Number of positive eigenvalues of M counting multiplicities with let A be an n by n real symmetric matrix. A be an n by n real symmetric matrix. Q be an n by n real invertible matrix. Real invertible matrix. Then the which options are correct? The first one, rank of A equal to rank of Q transpose AQ. Rank of A equal to rank of Q inverse AQ. Number of positive eigenvalue of A equal to number of positive eigenvalue of Q transpose AQ. Number of positive eigenvalue of A equal to number of positive eigenvalue of Q inverse AQ. Okay. So it's also a very simple problem. Little bit of a small concept we need for this, for take which one is correct. Okay. So we know that first of all small concept already well familiar. Okay, so we know that when a matrix is multiplied by a non-singular matrix, some matrix are there, when you multiply the non-singular matrix, okay, non-singular matrix, the rank of the matrix will not be changed. It's a small result already well familiar. It's a very easiest one. Okay, இது எல்லாருக்கும் தெரியும்னு நினைக்கிறேன். ஒரு மேட்ரிக்ஸை ஒரு நான்-சிங்குலர் மேட்ரிக்ஸ் கூட மல்டிப்ளை பண்ணால் the rank வந்து மாறாது. அப்படின்னா Q be the invertible matrix அவங்க கொடுத்துட்டாங்க. Invertible means non-singular matrix. Qன்றது non-singular matrix. Qன்றது non-singular matrix. Q inverse Q transpose is also an invertible matrix. Okay, so Q inverse Q transpose is also invertible matrix. Okay, so from this rank of A equal to rank of Q transpose AQ. Because of Q transpose AQ, the rank of the Q transpose AQ should be equal to rank of A. Because of when you multiplied any non-singular matrix, any matrix with a non-singular matrix, okay, ஒரு மேட்ரிக்ஸை ஏதோ ஒரு நான்-சிங்குலர் மேட்ரிக்ஸ் கூட மல்டிப்ளை பண்ணால் ரேங்க் மாறாது, ரேங்க் டசன்ட் சேஞ்ச். அதனால் ரேங்க் ஆஃப் ஏ ஈக்குவல் டு ரேங்க் ஆஃப் கியூ டிரான்ஸ்போஸ் ஏக்யூ. அதே மாதிரி ரேங்க் ஆஃப் ஏ ஈக்குவல் டு ரேங்க் ஆஃப் கியூ இன்வர்ஸ் ஏக்யூ. ரேங்க் ஆஃப் ஏ ஈக்குவல் டு ரேங்க் ஆஃப் கியூ இன்வர்ஸ் ஏக்யூ. So option 1 and option 2 both are correct. Okay. The next for the option 3 we need the small concept. Once again another small concept. Already discuss பண்ணிருப்போம்னு நினைக்கிறேன். The congruent. What do you mean the congruent? When you said the two matrices are congruent. two square matrices A and B over a field are congruent if there exists an invertible matrix P such that P transpose AP equal to B. P transpose AP equal to B. This satisfy pannuchuna, then A and B are called the congruent. Sir, edhukku sir ipo congruent matrix பத்தி discuss பண்றோம்னா we need the Sylvester's law of inertia. That means two congruent symmetric matrices with real entries have same number of positive, negative and zero eigenvalue. ரெண்டு congruent symmetric matrices இருந்ததுன்னா with real entries have same number of positive, negative and zero eigenvalue. இது அப்ளை பண்ணுறதுக்காக தான் congruent definition பார்ப்போம். Here நமக்கு given the hypothesis ABN real symmetric matrix. Another one QBN n by n real invertible matrix. Okay, n by n real invertible matrix. It's a very important real matrix. Both are real matrices. From this, for the option 3, I will express A equal to Q transpose whole inverse into Q transpose. What is the Q transpose whole inverse into Q transpose? Identity matrix. A Q into Q inverse. Q into Q inverse is also I matrix. So I A I. It's called the A. So A equal to Q transpose whole inverse Q transpose A Q Q inverse. Once again A equal to the Q transpose whole inverse or the A transpose whole inverse equal to A inverse whole transpose. And that property, there is a property of the inverse of the matrix. Okay, so Q transpose whole inverse we can express Q inverse whole transpose. Q inverse whole transpose. Abna into Q transpose AQ into Q inverse. Enna pandrom? Use the bracket for the middle 3 matrix. Use the bracket for middle 3 matrix Q transpose AQ. Why sir? அப்படினு கேட்டீங்கன்னா Q transpose AQ from this expression this is Q transpose AQ and A both are congruent symmetric matrix with real entries. Congruent symmetric matrix with real entries. Q transpose AQ and A are two congruent symmetric matrix with real entries. Because of this is considered as the P transpose something B, this is P transpose B P equal to A. From this A and B are congruent symmetric matrix. Two matrix are congruent symmetric matrix with real entries. The corresponding eigenvalue positive means ரெண்டுத்துக்குமே பாசிட்டிவாக தான் இருக்கும். நம்பர் ஆஃப் பாசிட்டிவ் ஐகன் வேல்யூ பாசிட்டிவாக தான் இருக்கும். நம்பர் ஆஃப் நெகட்டிவ் ஐகன் வேல்யூ நம்பர் ஆஃப் நெகட்டிவ் ஐகன் வேல்யூ சேமாக தான் இருக்கும். நம்பர் ஆஃப் ஜீரோ ஐகன் வேல்யூ நம்பர் ஆஃப் ஜீரோ ஐகன் வேல்யூ சேமாக தான் இருக்கும். ஃப்ரம் திஸ் lambda plus of A equal to, that means number of positive eigen value of A equal to number of positive eigen value of Q transpose AQ. So option 3 is correct. Okay, so the next one for the option 4 we need the another small concept, similar matrices. In a linear algebra, two n by n matrices A and B are called the similar matrices if there exists an invertible matrix P such that B equal to P inverse AP. B equal to P inverse AP. Okay, so congruent means P transpose AP. The similar means P inverse AP equal to B. That's a small difference. That's all. Okay, so for the option 4 we can express the A Q into Q inverse AQ Q inverse. Because of Q into Q inverse I, Q inverse is also I. So A என்றது A தான், I is also A. So A equal to like that. And then A equal to using the bracket for the middle 3 matrix. So Q into Q inverse AQ into Q inverse. So from this what is the conclusion? Q inverse AQ and this A are similar matrices with real entries. Similar matrices with real entries. Already well familiar another result in the similar matrix on the similar matrices. Eigenvalues of the similar matrices are equal. Eigenvalues of the similar matrices are equal. From this number of positive eigenvalues of A equal to number of positive eigenvalue of Q inverse AQ. So that option 4 is correct. So lot of concept needed to this problem. Similar matrices na enna theriyum, congruent matrices enna theriyum, Sylvester law of inertia na enna theriyum, இதெல்லாம் தெரிஞ்சால் தான் இந்த ப்ராப்ளத்தை நம்ம ஃபேஸ் பண்ண முடியும். ஸோ இதிலிருந்து நிறைய லேர்ன் பண்ணிக்கிறோம் ஃப்ரம் தீஸ் ப்ராப்ளம் நம்பர் 70 பர்டிகுலர்லி. இட்ஸ் அ வெரி வெரி இம்பார்ட்டன்ட் ப்ராப்ளம். ஓகே, தேங்க்யூ ஸோ மச்.